All right, everybody, welcome back. So basically today, with this lecture video number 2, I'm going to be picking up pretty much right where we left off with in class the other day. In class, we finished this entire example of CH4 together, the very stepwise one. Moved on to these two examples here, which were carbon tetrachloride, CCl4, and water, of course, H2O. And we finished class with those. We still have these two examples, though, so I want to start today's lecture video with these two examples, which are then going to kind of help us segue right into our next step of kind of building these Lewis structures, and these a lot more in-depth Lewis structures for these covalent molecules. So we're going to kind of add some more tools to the tool belt with the second half of this lecture video to help us do that. But now let's first, again, start with these examples here, right? So ammonia, which is NH3, again, the formula is given to you here. That's not always going to be the case, though, right? As we progress through this lecture, or not this lecture video specifically, but as we progress through chapter 10, you're just going to have to know what ammonia is, right? Ammonia being NH3. So it's one of the things you'll have to know. And same thing with CO2 down here. You will have to know that carbon dioxide translates to CO2 as the formula. And again, we will be doing a good job of kind of helping us through that. So now, formula is written out. Let's label things as metals, nonmetals, or polyatomic ions, right? Nitrogen, right-hand side of the staircase, so non-metal. Hydrogen, left-hand side of the staircase, but again, is our exception to the rule. It is still a non-metal. So we have two or more nonmetals bind to each other, so we have covalent bonding. Okay, nothing crazy to write home about now. Now, up next is our valence electron calculation. Right. Pretty easy. Looking at our reference table, again, we see that the electron configuration for nitrogen is 2-5, right? So 2-5, which means 5 is our number of valence electrons. So one atom of nitrogen is 5 valence electrons. When we look back at our formula, NH3, we only have one atom of nitrogen, so it's 5 times 1 to give us a total of only 5 electrons from that one nitrogen. Okay. Up next here, of course, is our hydrogen. Hydrogen just has a plain old configuration of just 1, right? Electron configuration of just 1. So that means the one and only electron it is its only valence electron. But in this case here, guys, there are 3 total H's, 3 total H's in our formula of NH3. So it's 1 times 3 to give us a total of 3 valence electrons. So we add this together. 5 plus 3, of course, is going to be 8 valence electrons. Okay, so that's the number of valence electrons we are going to use to help us build this molecule of NH3. Again, write a skeletal structure, right? Draw a skeletal structure. It always starts, of course, with making sure that we've got our central atom in this case being nitrogen, right? There's only one nitrogen present here compared to the 3 hydrogens. So if there's only one of that particular substance, we go ahead and put an N there because that's our central atom, right? Now our goal for our skeletal structure is to add all of our other atoms in space here. We did our 1N. Now we have to place our 3 H's. Again, our formula is NH3, so we have 3 H's to place, right? Again, making sure to place our H's in space in the exact 4 different places, right, you can place, right? I did 3 of the 4 because we only have 3 to place, so that is my skeletal structure for NH3. Next up, I have to then add my electrons, my valence electrons, to my Lewis structure here. Again, my recommendation is always start by giving your central atom its 8. Making sure to bond when you see things to bond, and making sure to use dots, right, pairs of dots when there's nothing to bond. So looking to the right of nitrogen, there is another atom here, so we should make sure we use a single bond to bond these. When I look above nitrogen, there is another atom here, which is H, so I'm going to use a single bond. When I look to the right of nitrogen here, there's another H here, so another atom to bond to. Now, when I look below nitrogen, however, there is no other atom to bond to. So in this case here, since there is no atom to bond my nitrogen to, I still have to give it its 8. So I finalize it by putting my 2 dots right there, right, my lone pair. There was nothing below nitrogen to bond to, no H's, no nothing. So because of that reason, we had to use a lone pair, right? Now, when I look, I had a total of 8 valence electrons in total to use. When I look at all of my pieces here, each of these single bonds were 2, 4, 6 electrons in total, and then 7, 8. So I now have 0 electrons here to use. All right. Now, going back and doing our checks, right? We have to make sure that each of the atoms present in my molecule have hit that octet rule, that rule of 8. So when I look at nitrogen, for example, right, I circle everything that is being shared between my nitrogen and my other stuff here. I don't know what's going on here. And I look at that, right? So 2 from this bond, 4, 6, 7, 8. So a total of 8 electrons are on my nitrogen. When I look at my hydrogens specifically, I look at this hydrogen here, looking at this hydrogen here, I'm looking at this hydrogen here. Oops, let's draw a better circle actually. Okay. Inside of each of these circles here is one single bond here, right? Again, because everything that happens when it comes to a bond, a covalent bond that has formed, represents the sharing of electrons, right? So although these bonds, the 2 electrons in each of these single bonds, were used for nitrogen, they're also being shared and then therefore can be used for the total count for hydrogen, right? Because they're being shared. So each of these hydrogens only have one single bond attached to them, which means they're only sharing 2 total valence electrons. But again, if we remember, hydrogen, like everything else, okay, and like 9 times out of 10, hydrogen is the exception. Hydrogen only needs 2 valence electrons as opposed to the 8 with other ones, right? So because of that reason, H, H, and H, all 3 of these H's are good to go. So yes, this is a good Lewis structure. This is the Lewis structure for ammonia, NH3, okay? Next up here is going to be our carbon dioxide, right? Again, I give you the formula for right now, but again, in the future, you might not be given the formula, so CO2. Carbon is a non-metal, right side of the staircase here. Oxygen is also a non-metal, right side of the staircase. So 2 or more non-metals bond to each other. Once again, type of bonding we have here is covalent. Next up is to add up the valence electrons. Same as always, C and O. Go to the periodic table, find the Lewis structure, find the electron configuration for each of these guys here for carbon and oxygen. Right, looking at the configuration for carbon is 2-6. No, sorry, 2-8. 2-8? No, goodness, sorry. 2-4. 2-4 is our electron configuration for carbon. So that 4, being all the way to the right, is our number of valence electrons in an atom of carbon. Okay. What about for oxygen, right? Oxygen is the 2-6, right? So oxygen has a total of 6 valence electrons in it. Okay. Looking back at the formula, I've only got 1 carbon to deal with here, so it's 4 times 1, giving me a total of only 4 electrons coming from my 1 carbon. Okay. Well, what about oxygen? All right, I've got a total of 2 oxygens, right? Because this subscript of 2 tells me how many 2s or how many oxygens I have. So 6 times 2 in this case here. Ooh, I don't know what's going on here. Why is it zooming in? No, I don't want to zoom in. Oh my God. I have no idea what's happening here, guys. All right, we're back. I'm not sure what happened there, but we are back. So again, 2 oxygens to deal with, so it's 6 times 2, meaning 6 times 2, of course, is 12 total electrons coming from our 2 oxygens. So 4 plus 12 gives us a total of 16. Okay, 16 total valence electrons to deal with this Lewis structure. Now, same thing as always, moving right along after our valence electron calculation, moving right along to our skeletal structure here, again, which always starts with our essential atom. So go back to our formula over here, and again, whichever element, we only have 1 atom of it, that is our essential atom. We've got a total of 1 carbon and 2 oxygens, so we've only got 1 carbon, that is our essential atom, okay? Now, I can place these oxygens wherever I want. I'm just going to choose to place my oxygen on the right and the left here like I've done so. Okay, left and right. Now again, last thing to do here is to add my electrons. I've got 16 to add here. Again, always starting with your essential atom of carbon. All right, so let's go ahead and do that, right? Again, to the left of my carbon is an atom of oxygen, so I'm going to make sure I bond these guys together with a single bond. Above my carbon is nothing, so dots. Okay, again, whenever there's nothing, put dots. To the right of my carbon is another atom of oxygen specifically, so I have to make sure I bond these 2 atoms together. And then below my carbon here is nothing, right? So I want to make sure that I put dots here when there's nothing to bond, right? If there's something to bond, covalent bonds. When there's nothing to bond, nothing to bond there, so you just use lone pairs. So in doing that, right, these 2 bonds and these 2 lone pairs here, I've used a total of 2, 3, 4, 5, 6, 7, 8 total electrons. Okay. So take away 8 from here, and we've got 8 more valence electrons to utilize. All right, so now, again, since our carbon has its 8, we don't want to place any more than that around our carbon there. Okay, I'm just going to clean this up a little bit. We don't want to place any more electrons around this carbon here. So everything, the remaining 8 have to go on this oxygen and this oxygen. So let's go ahead and do that, right? There's nothing else this oxygen wants to bond to. So we're just talking straight up dots here, right? Just lone pairs, right? So nothing above oxygen, so lone pair. Nothing to the left of oxygen, so lone pair. Nothing to the below oxygen here, so lone pair. So in doing that, I've just placed 1, 2, 3, 4, 5, 6 total electrons here. So I've only got 2 electrons left, and maybe your gears are turning already, but let's see if they are now. So I got to place my 2 around here, so I've only got 2 left to place, and that is it. Okay, I can only use a maximum of 2 more electrons, and I just did that. So we have no more electrons to utilize, so I've got 0 electrons left. Now let's go and do my count to see if I did this correctly, right? Let's see if this Lewis structure is correct. Again, if I isolate just carbon here and look at everything centered around carbon, I've got 2 electrons from this bond on the right, 2 more electrons for a total of 4 from this bond on the left here, 5, 6, 7, 8. So yes, okay, carbon got its 8. We're in the money there, okay. What about this oxygen on the left-hand side here? Whoopsie. This oxygen on the left here. All right. So a total of 2 coming from this bond here that was between carbon and this oxygen. So 2 from this bond, 3, 4, 5, 6, 7, 8. So it got its 8. We're good to go with this oxygen. Looking at this last oxygen over here, though, we shall see. All right. So when we look at this bond here, okay, there's 1 bond centered around this oxygen here. So 1 single bond means 2 oxygen or 2 electrons. So 2 electrons, 3, 4. We only have 4 here, which is not good. Oxygen needs 8. So what the heck do we do? Well, guys, this is where this idea of double bonds come into play here. All right. So in actuality, what you're supposed to do is use double bonds. Okay, we use double bonds to get what we want here. In this case here, we're going to do a little bit of reorientation with the electrons we had here. Place my lone pairs there. Create double bonds here. Like that. Okay. Pairs there. Lone pair, or actually, let me clean this up a little bit. Boom, 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 boom. Lone pair above, lone pair below. Lone pair above, lone pair below. 1 pair above, 1 pair below. All right, so now this is a correct Lewis structure for CO2. All right, well, what the heck did Mr. Serra just do, right? Why is he talking about double bonds? We've never heard of these before. You might have in lab, okay, more recently, but again, double bonds, what the heck do they mean? Well, for starters, get this down, okay, because this is a correct Lewis structure for our CO2 here, right? So let's exit this drawing here, move on to right here, okay? Different types of covalent bonds. Well, again, guys, up until this point, we have not yet dealt with anything other than a single bond, right? A single bond is a sharing of 1 pair of electrons, 2 total electrons, between 2 atoms symbolized by 2 dots or 1 line. And again, generally in this case, it's going to just be 1 line. Well, in covalent molecules, there are sometimes going to be situations where 2 different atoms are going to be bonded together using more than just a single bond, either a double bond or a triple bond. And again, if you guys have done lab, which up until this point, I think all of you guys have done the covalent molecules lab, you guys actually would have created your own double and triple bonds using those metal springs, right? So when we look at this double bond here, double bond is the sharing of 2 pairs of electrons for a total of 4 between 2 atoms symbolized by either 4 dots or 2 lines. Again, more often than not going to just be 2 lines. We're very rarely going to use dots to represent double bonds or bonds in general, okay? And lastly, of course, is a triple bond. Okay, a triple bond is the sharing of 3 pairs of electrons, so a total of 6 electrons in that one bond between 2 atoms symbolized by either 6 dots, which again, probably not the dots, or 3 lines. So single bonds look just like what we've been utilizing them as, right? Single bond looks like that. Double bond looks like what we saw on the previous slide with CO2, and triple bond looks like this, okay? Literally 3 lines, all like that. So single bond, double bond, triple bond, that is exactly what we are dealing with here with the different types of covalent bonds, okay? Now, polyatomic ions and Lewis structures, yes, they are going to be useful. They are going to be something we're going to have to, work on, but we're going to kind of save this for class. So Yeah, there are going to be situations, guys, where in covalent molecules, you are going to essentially have to build a covalent molecule out of a Lewis structure. And again, we'll talk more about that in class. Okay, see you later.